Hello, my name is Su Hui. I'm a PhD student from Cardo School of Mines. In this presentation, I'm going to talk about our recent work on scaling infeasibility proofs via concurrent, Codimension-one, locally updated Coxeter Triangulation. A lot of the tasks we do in real life are in very confined workspace. Examples range from household tasks, such as organizing a cupboard and grasping things from back of the fridge, to more professional tasks, such as house framing and engine compartment checking. In all of these tasks, it is possible that a plan to reach the target location does not exist, and it is hard to decide whether a plan exists or not by just looking at the workspace. This means besides finding a plan, the robot also needs to know whether the plan exists or not. This is the completeness property for motion planners. A complete motion planner can find a plan or report plan non-existence in finite time. However, this completeness property is hard to achieve for high-dimensional motion planning problems. So people usually go for weaker notions of completeness. For example, widely used sampling-based motion planners are probabilistically complete, meaning they can find a plan given long enough time. But when plan does not exist, they would run forever or until a given timeout. This work focuses on providing this infeasibility information alongside a sampling-based motion planner. Having completeness in motion planning is especially important in task and motion planning, where we have a multi-step task plan, and for each task plan, we have a corresponding motion plan. In task and motion planning, an important part is how to integrate the discrete task space and the continuous motion space. If the motion planner cannot provide past non-existence guarantee, then it would create a lot of dilemma between the task planning layer and the motion planning layer. To summarize, we need a general motion planner that returns a plan when plans exist and reports past non-existence when plan does not exist. The problem is a general motion planning problem setup. The inputs are the robot's configuration space, a start configuration, and a go configuration. The output is a plan if a plan exists, or an infeasibility proof if a plan does not exist. And here we define infeasibility proof as a manifold that satisfies these three requirements. First, it needs to be closed. Second, it needs to exist entirely in the obstacle region. And third, it needs to separate the start and the go. In our previous work, we have developed an algorithm that constructs infeasibility proofs for up to 4 DOF manipulators. The algorithm has two main steps. The first step learns a manifold in a configuration space that separates the two regions. Then, we triangulate the manifold to make sure it's entirely in the obstacle region of the configuration space. We have also proposed the narrow passage motion planner called Sample-Driven Connectivity Learning, or SDCL. This algorithm uses the learner manifold to generate manifold points. If there are manifold points in C3, then these points are very likely to be narrow passage points. We add these points as samples to improve narrow passage motion planning. In this work, we scale infeasibility proof to higher dimension through the following changes. First, we adapt Codimension-one Coxeter Triangulation into our framework. Secondly, we parallelize Coxeter Triangulation on multi-core CPU. And then, we locally update the triangulation when parts of it is not in the obstacle region to save triangulation time. We also integrate SDCL for narrow passage motion planning. Lastly, we have a new bisection step for checking all facets of the triangulation. Here is the general algorithm overview. The inputs are the configuration space, the start configuration, and the go configuration. The algorithm runs 3 threads in parallel: the PRM thread, the SDCL thread, and the proof construction thread. The algorithm terminates with either an infeasibility proof or a plan. Next, we will discuss the proof construction thread in more detail. Coxeter triangulation generates an Rn triangulation. Then it finds intersecting line segments and their intersecting points with the manifold. The line segments and their intersecting points form the final triangulation. This structure of Coxeter triangulation makes it great for parallel implementation. Next, we talk about the local update step. If there are parts of the current manifold and the triangulation in C3, then we retrain the manifold and project to the new manifold so that the updated triangulation exists entirely in the obstacle region. We run experiments on 4DOF and 5DOF manipulator scenes. The table shows the runtime result. 4DOF experiments complete within seconds, and 5DOF experiment completes within minutes. Here is the profiling result, and we can see that the triangulation and checking takes the majority of runtime, and this is what we are focusing on right now. And here I want to show our roadmap throughout the years on infeasibility proofs. We have shown steady results with increased dimensionality. In this work, we integrated SDCL and proved infeasibility for 5DOF manipulators. In our most recent results, we have moved triangulation and collision checking to GPU, which gives us 2 orders of magnitude speed up. And 5DOF infeasibility proof now can complete within seconds. 6DOF is really promising. Here's a summary of this talk, and thanks for listening.